Okay, I think we can start. Hello, everybody. I'm Ray from Certora, and I'll be introducing Garand from Stellar, presenting Solving State Bloat with State Archival. Thank you very much.
Howdy. My name is Garand, and I work on protocol for the Stellar network. And today I'll be talking about State Archival, our novel protocol solution to the state bloat problem. In particular, I'll be talking about the novel attack surfaces that this protocol introduces and some of the mitigations we've taken against those attacks. So I'll begin by giving a brief description as to what the state bloat issue is, and then how State Archival works at a high level. And then I'll delve into 3 specific attack vectors and describe how we defend against them. So first, the problem, state bloat. Now today, because we are in Thailand, I've chosen Mudang as the mascot for the state bloat problem, or more specifically, a Mudang coin. So the issue that the Mudang coin highlights is that of state bloat. Now the issue is, on public blockchains, all state must be maintained indefinitely. And any transaction that writes state to the blockchain pays a one-time fee for this indefinite storage. The issue is that this one-time fee when submitting a transaction has a reoccurring cost on the network. Now the Stellar network is one of the oldest layer 1 blockchains in existence. We've been around for over a decade. And you can imagine in that 10 years, we've gotten a lot of meme NFTs and meme coins like Mudang that aren't actively being used, but we still have to store them indefinitely. Now the problem is, unlike Web 2 databases, because you have to hash all blockchain state, traditional DB caching is not effective. This is primarily due to Merkle structures, and in order to update a Merkle structure, you must do an arbitrary number of blocking reads on completely random state, even if you're not actually using that state in transactions. What this means is that the result is that DB size will increase indefinitely, and there's essentially 0 ways to efficiently prioritize other information. So for instance, your USDC, in this case, cannot be prioritized over your Mudang coin. And so the solution to this is State Archival. So unfortunately, we're going to have to kiss our mascot goodbye. So with State Archival, each piece of ledger state is given a TTL value. Now when this TTL can be extended via what we call rent payments. Now what the rent payment system does is it essentially reconciles the fee system, where we have a reoccurring rent cost to now match this, or a reoccurring rent fee to match this reoccurring cost that the storage puts on the network. Now after a TTL expires, the entry is archived and actually deleted from validator databases, freeing up these resources. And any transaction that touches an archived piece of information immediately and atomically fails. But don't worry, even if an entry has been archived and deleted, it can always be restored back to the ledger and used again. To do this, we store all archived state off-chain in a series of immutable Merkle tries. Then, if you want to reuse that state again and restore it, you can do so by providing a Merkle-style proof of existence to validators. Now, to demonstrate how this works, let me give an example as to how we construct these archival Merkle tries. So here what I have is an example of a data or the validator state at the very beginning of State Archival before we've turned it on. And you can see here that we have a validator on-chain with a bunch of entries that have live TTLs and an empty archive off-chain. Now some time will pass, and eventually these TTLs will expire. And so we see the first entry expires. What we're going to do is we're going to remove this entry from the live ledger state and put it in what we call the hot archive. This is a Merkle try stored locally on validator databases. And so we haven't actually deleted the expired or archived state yet from validators. It's still maintained locally for now. And so we have this Merkle try here. Some more time will pass, another entry will become archived, be removed from the live state, and add to this hot archive. Now at this point, the hot archive is considered full. And so what we're going to do is persist just the Merkle root of that tree, and then delete the rest of that Merkle try, and now publish it to the off-chain archive database. And so what we're left with is a validator that only maintains the Merkle root of this archive try, but not the actual archive state. This process then continues recursively, and you can imagine that over time, the validators store many Merkle roots, and then we have many Merkle tries in the off-chain archive. So this is the high-level design. Now I'd like to talk about a couple of the particular attacks that this exposes and how we defend against them, beginning first with what we call the double restore attack. So in the double restore attack, consider that I'm an attacker that has a 10 USDC balance, and I'm going to allow this to become archived as TTL expires. So here we have an image of what the archival try looks like. I have my 10 USDC balance in the first archive try 0 that's off-chain. So I'm going to then restore my 10 USDC by providing a proof of inclusion to this Merkle try to the validator. Now, because the validators maintain the Merkle root, they can ensure the integrity of this entry and actually prove that the 10 USDC really does exist. So it gets restored. Now, I, the attacker, will spend 5 of my recently restored USDC and allow the new entry, which now only has a 5 USDC balance, to become archived again. And so with this new 5 USDC value will become archived, but it will be in the next new archival try. Remember, because each of these Merkle tries is immutable, we can't actually remove the 10 USDC leaf once it's restored. And now I, as the attacker, have a new up-to-date 5 USDC balance in archive try 1 and an outdated 10 USDC balance in the older try. And what I'm going to do is, instead of restoring the new balance like I should, I am going to restore the outdated 10 USDC balance, and it will now essentially result in a double spend. Now, the validators have no way of knowing that this is an incorrect value because a valid Merkle proof of inclusion does exist. And so to defend against the double restore, what we're going to do is we're going to require a more complicated proof system. And so just like before, if I want to restore an entry that's currently archived in try n, I will have to include a proof of inclusion for try n. Additionally, I'll have to provide a proof of non-inclusion for the given key in every newer try. What this does is it enforces that only the newest version of an entry can be restored at any given time. Now, this does come with one unfortunate performance caveat, and that is, in order to prevent against a double restore, we need to write both archived entries as well as deleted keys to the archive. You can imagine if I restore my 10 USDC, spend it all such that the key is deleted, I don't want to be able to restore that 10 USDC balance a second time in double spend, so you have to record both the archived entries themselves as well as the keys of deleted entries so that you have protections via this proof of non-inclusion property. The second attempt, or the second attack, is malicious archival. And so in this scenario, the attacker is going to take out a loan, and that loan is going to have some token balance as collateral. Now, as the attacker, I'm going to purposefully let my collateral become archived such that its TTL expires, and I'm going to then default on my loan. Now, the loan provider actually cannot collect that collateralized material because it's in the archive, and they don't have the private key in order to restore that entry. And so to prevent this type of attack, what we're going to do is consider that all TTL extensions and restorations do not require private keys, state ownership, or any sort of authorization. Now, this is generally fine. It has no drawbacks. There is really no negative impact to having an arbitrary member extend the TTL or restore an entry they don't own. There's nothing negative this can do, and it allows the liquidator, in our case, to restore someone else's state that they defaulted on. The only issue with this is that smart contracts cannot use the TTL value for security enforcement because any arbitrary party can extend that TTL. So you can't use TTL to enforce like a signature expiration in this case. That's fine because there's much other design paradigms that smart contracts can use to enforce these properties. The final attack I want to consider is what's called the double nonce attack. And so in this attack, I'm going to have a victim that creates a nonce, a deterministic key, and that nonce is going to become archived. Now, what the attacker is going to do is, instead of restoring the nonce value that does exist in the archive, it's instead going to recreate the nonce at the exact same key, but with a different value. Now, the issue is the validators have no way of actually preventing this because the validators don't know what keys exist in the archive. And what the result is that this is an eclipse attack, where the attacker has a valid nonce live on the ledger state that actually eclipses the legitimate value stored off-chain in the archive. And so to prevent this, what we're going to do is kind of like we required proofs of non-existence in restoration cases, we are also going to require proofs of non-existence when creating a new key for the first time. In particular, when creating a key for the first time, you'll have to prove that that key does not exist in every single try in the archive. Obviously, this is really inefficient and not a very good situation for the end user, so we're actually going to optimize away the proofs of non-existence. And so for each Merkle try, in addition to holding the root node persistently, validators are also going to store a binary fuse filter set of all the archived keys. A binary fuse filter is just an optimized Bloom filter. Now, the binary fuse filter does produce a false positive because it's a probabilistic set, but the properties of the binary fuse filter are such that it favors safety over liveness. What this means is that a false positive will sometimes not allow restoration of a valid entry, but it will never allow restoration of an invalid proof. Now, in the event of a false positive, you can always provide the real full proof of non-existence to override the false positive such that liveness can still be maintained. Now, the reason we use binary fuse filters is that they're super efficient, and this has essentially zero storage overhead compared to the space savings we would have if we stored all of these archived keys as a traditional set. So where are we at? This is not a theoretical work. We've actually implemented this. So earlier in February, we launched the interface for smart contracts on mainnet, and currently the full proof system with entry deletion is code complete and is expected to hit mainnet later in 2025. Thank you very much. If you have questions, you can of course follow me on GitHub